Hello friends, in this video let us discuss about the working principle of DC generator. So basically there are two types of generators available, one is AC generator and the other one is DC generator. So whatever may be the type of generator you are having, they receives mechanical energy as input and delivers electrical energy as output. So they receives mechanical energy from a prime mover to which it is coupled and delivers electrical energy are your generators. So the AC generator gives you the three-phase AC power and the DC generator gives you the DC output. So both of these generators, either AC or DC generator, that depends on the Faraday's laws of electromagnetic induction, which says that when a conductor is placed in a moving magnetic field or whether a moving conductor is placed in a magnetic field, whatever it is immaterial whether you are moving the magnetic field or whether you are moving the conductor, but one thing should vary in both of them. Then there will be induced EMF in the conductor, and if the conductor is a closed loop, then this closed loop helps you to circulate the current in that loop, and the magnitude of the induced EMF for the flux cutting, that is the magnitude of induced EMF depends on the rate of flux cutting across the conductors. So if there is more number of flux lines passing through the conductor, that means the magnitude of induced EMF is more, and if there is less number, then the magnitude of induced EMF is less. So it is directly proportional, you can say, from Faraday's electromagnetic induction law. EMF, that is induced EMF, is directly proportional to the rate of change of flux. So more the flux cutting, more the induced EMF, less the flux cutting, less the induced EMF. Now, let us understand the working principle of your DC generator by taking a single turn rectangular loop ABCD placed in between two opposite magnetic poles. Let us say this is my north pole and this is my south pole. Now, let us rotate this rectangular loop ABCD against the axis AB, and here if you look at the rectangular loop from a 3D diagram or 3D point of view, then this rectangular loop appears in a vertical position, and at this vertical position the tangential motion of the conductors, say AB and CD, are just parallel to the magnetic flux lines. So when they are just parallel, that means if you are having a conductor like this and the magnetic lines of that is the magnetic flux lines are passing through this, and there are no flux lines cutting your conductor, so they are moving parallel, that is your conductor is parallel to the flux lines, so there will be no flux cutting here when they are just parallel to the magnetic flux lines. So the conductor AB and CD at this vertical position, as they are parallel to the flux lines, there will be no flux cutting, that means no induced EMF, that means no induced current can be observed in this loop ABCD. Now let us start rotating this rectangular loop in clockwise direction. So if I rotate my rectangular loop to further 90 degrees, then this will be the position of my loop where ABCD is at the top here, it is coming in front of the south pole, and the CD, which is at the bottom here, is coming in front of the north pole. And again, if you see the direction of force line, that is the magnetic flux lines, will be like this from north to south. And here if you see from a 3D point of view, the conductor CD and the conductors AB are just perpendicular, that is the tangential motion of these conductors, because we are rotating in this direction, and the tangential motion of these conductors are just perpendicular to the magnetic flux lines. So when they are just perpendicular to the magnetic flux lines, that means you are having the rate of flux cutting is maximum. So you can witness maximum flux cutting, and as you are having the rate of maximum flux cutting, then the induced EMF is maximum, and as the conductors, or you are having the conductors AB and CD are forming a closed loop, that means the induced current can be seen in these conductors, in this rectangular loop, you can say. Now the direction of this induced current can be determined from your Faraday's, that is it is a Fleming's right hand rule. From the Fleming's right hand rule, you can determine the direction of induced current by knowing the direction of magnetic flux lines and the direction of motion of the conductor. Now if I say I am having a magnetic poles, if I say this is my magnetic pole, this is my south pole and this is my north pole, that means the direction of magnetic flux lines from north to south is in this direction, and I am placing a conductor, that is I am forcefully bringing a conductor under this magnetic field, and if I say the direction of force is acting in this way, this is my direction of force and this is the direction of magnetic field, then the direction of the induced current will be mutually perpendicular to both of these quantities. So if you, according to the Faraday's right hand rule, if you stretch your right hand thumb finger, index finger and the middle finger perpendicular to each other, so the thumb finger shows you the force acting on the conductor, or the direction of motion of conductor you can say, and the middle finger, this is your the index finger, so the index finger shows the direction of magnetic field and the middle finger shows you the direction of induced current. So by knowing the two quantities, the force and the magnetic field, you can find the direction of induced current, and the direction of induced current will be perpendicular to the direction of motion of current or the direction of force and the direction of magnetic field. So this is your Fleming's right hand rule. Now if I say the force is acting in this direction and if I stretch my hand, so the thumb finger is the force and the index finger is the magnetic field and the middle finger shows me the direction of induced current, so I know this is a force, this is a magnetic field, then the induced current will be acting in this direction, that is a perpendicular to both of this magnetic field and the direction force acting on the conductor. This is your Fleming's right hand rule. Now what is the difference between the Fleming's right hand rule and the Fleming's left hand rule? The Fleming's right hand rule is basically applied in the generators where you know the direction of magnetic flux lines and the direction of force acting on the conductor. So here you are going to find the direction of induced current, but in Fleming's left hand rule, there you know the direction of induced current and you know the direction of magnetic flux lines, and you are going to find there the direction of force acting on the conductor or the direction of motion of the conductor. So generally this rule is mainly applicable to your electric motors, and FRR is mainly applicable to the electric generators. So by applying Fleming's right hand rule here, I can see the direction of current from C to D and from here A to B. So as you see, as you turning or as you tilting your rectangular loop from 0, let us say 0 degrees, that is the parallel, it is parallel to the magnetic flux lines, and I am saying 0 degrees, and when I am turning to 90 degrees, what is happening is the angle between the magnetic flux lines and the motion of conductor is increasing from 0 to 90. So as you are increasing from 0 to 90, the induced EMF is also increasing. So if I say at reference position I am having the 0 induced current, and as I am increasing my angle at 90 degrees I am having the maximum flux cutting, that is the maximum induced current. And again if I tilt or if I rotate my rectangular loop ABCD to another 90 degrees clockwise, then this will be my position of rectangular loop. So again here I am having the north pole, and again here I am having a south pole, and similarly from this mode you can see the conductors CD and AB are just parallel to the magnetic flux lines. So that means there will be no induced EMF and no flux cutting, that means no flux cutting, no induced EMF, no induced current. So again here you are having the 0 current. So as you rotate again 90 degrees, again you are having the current as 0. Now again further if I rotate my rectangular loop ABCD to 90 degrees, I am rotating this rectangular loop to 90 degrees, then the tangential motion of the conductors AB, CD are just perpendicular to the magnetic flux lines. So this will be north pole and south pole. So they are just perpendicular to the flux lines. That means there will be maximum, the rate of flux cutting is maximum, that means more induced EMF, and that means you as a conductors are closed circuit, that means you are having the induced current in your rectangular loop ABCD. Here you can see the conductor, the loop side CD is in front of the south pole, and here the loop side CD is in front of the north pole, and whereas AB is in front of the south pole, here the AB is in front of the north pole. And again applying Fleming's right hand rule, the direction of current will be like this and the direction of current will be like this in CD. So by observing these two, you can see that the current is flowing from C to D here, and the current is flowing from D to C here, and here the current is flowing from A to B, whereas here the current is flowing from B to A. That means the direction of current is going to be altered, or you can say reversed. So again here I am having the maximum current in opposite direction, and if I further rotate this rectangular loop to 90 degrees, again I will reach this position. That means again I am moving to 0 degrees. So during every 360 degrees revolution, 360 degree revolution, I can see a one full sine wave. So where the maximum current in one cycle I am reaching the maximum current in positive direction, and in the other cycle I am reaching the maximum current in negative direction. So however, whenever the current you say conductor side AB is in front of the north pole, here also the conductor CD is in front of the north pole, the current direction remains same on these two loop sides, and here also whenever the AB is in front of the south pole and DC is in front of the south pole, the direction of current remains same for both these conductors. But as after 180 degrees turn, the direction of current is going to be altered. That means, so how can we use this alternating current to generate the DC output? Now normally in AC generators we are using the slip rings. Here we connect two slip rings, and the brushes riding on the slip rings can be connected to the load terminals, and you can see the alternating current in the load circuit. But here to convert this reverse current to direct current, so I need the basic output is like this. So the basic output I need is in this form. So this current has to be reversed now. So this current can be reversed by taking commutators or by connecting commutators at the cut part of this loop. Now if I cut here and connect two commutator segments, I am connecting two commutator segments. The commutator segments are nothing but the cylindrical copper rings insulated from one another. They are also known as split rings because they are split into two halves or two segments, and they are insulated from each other. And I am placing two stationary brushes on this commutator segments, and I am connecting it to a load circuit, that is a resistive circuit. So here what is happening is, if I say this is my brush, this is my brush 1, and this is brush 2, and this is A, and this is B. Similarly, let me connect my two commutator segments here. I am connecting two commutator segments basically to alter the direction of reverse current. So if I alter my direction of reverse current, then I will be having a DC output from this DC generator. So this is my load circuit, and again I can say this is my brush A, this is commutator segment A, this is commutator segment B, this is brush 1, and this is brush 2. They are connected to the load circuit, say resistive circuit. Now here if I see the current is flowing from A to B, and it will pass to the commutator segment B, flow from brush 2 to this. If I say this is L and this is M, this current is flowing in the load circuit from L to M. This is my direction of current. Now here again if I see, as the direction of current is reversed, so basically the current direction is going to be like this for 360 degree revolution. So what I am doing here is, again if you see the load circuit, the current will be flowing from this direction if there are no commutators. But what your commutator segments are doing is, the commutator segment B, as the loop turn, as the armature turn rotates, then along with the armature turn the commutator segments are rotating. So again after 180 degree rotation, after 180 degree turn, the commutator segment B is coming attached to the brush 1, and the commutator segment A is going to get attached with the brush 2. So brush 1 is attached with the commutator segment B, whereas here the brush 1 is attached to the commutator segment A. So as the current is reversed and if you are reversing the terminals of the armature with respect to the external circuit by changing the commutator segments with the brushes connected, so the brushes are stationary here, only the commutator segments are revolving along with the armature turn. So these commutator segments reverse the armature terminals with respect to the load circuit. So I know the current is reversed, and again if I reverse the commutator segments or if I again reverse the armature terminals with the help of commutator segments, then I can again see the direction of current flowing from L to M. So here again I am having again if I see this reverse current is going to get altered in my positive direction. So this will be the waveform, this will be my DC output. So once I am repeating how the current is going to get altered. So initially the current is flowing from A, B, and this is positive, this is negative, from here to here. This loop, that is coming from here and moving to here. But what happens here is, as the current is going to reverse, because from B to A it is flowing, here from A to B the current is reversed, here D to C, here C to D, the current is reversed. Now I know the current is reversed, then if I reverse the terminals of my armature coils or armature turn, then after reversing it, I can make it reverse by changing or switching the commutator segments between the two brushes. So here the brushes are stationary, the brushes are the carbon or graphite brushes, and the brushes are stationary, but the commutator segments are altered. So after every 180 degree turn, the commutator segments are going to get altered. So in this way you are having the DC output, and see, the brushes are placed in such a way, the position of the brushes they placed in such a way that the commutator segments, whenever there is a change in the commutator segments, it happens when the magnetic flux lines are perpendicular to the plane of rotation of your coil. So whenever they are perpendicular to the plane of rotation of coil, there will be the switch over of the commutator segments across the two brushes, and the brushes will flexibly allow the change of commutators here. And if you are drawing a large amount of current, then there will be sparking produced in these brushes. Therefore we are mainly preferring the AC generator where we do not have the commutators, because we do not need to rectify the induced EMF, that is the induced EMF in the time varying induced EMF in the armature. So as no commutators are required in AC generator, we are more preferring AC generator nowadays, even though we need the DC output. So AC generators the AC power can be rectified to DC, and generally or mostly nowadays the DC generators are not being used because of the sparking problems occurring in the brushes and the commutator segments. But with the single turn you are having, the output you are going to get is pulsating in nature. So for getting a pure ripple free DC output, you can employ many number of coils. So many number of coils with many number of commutator segments you have to use for ripple free DC output, and you can also use the permanent magnets, and the coils can be wound on soft iron core for getting the ripple free DC output. So let us clearly once again repeat how the commutation is going here. So if I say this is my rectangular turn, and here these are two terminals, and if I say from here the current is, this is my positive terminal, the current is flowing from here to this part is your the commutator and the brushes part. I am not drawing it clearly. So this is your load circuit, and let me say this is my negative terminal. So current is flowing from this part to like this. So again, in the after 180 degree turn of my rectangular loop, what I am going to get? I am going to get the reverse current. Reverse current means the polarity is changing of the current. So here you see, for the other 180 degree turn, I am having the negative current. That means the positive can be replaced by the negative terminal now, and this will be my again here this part. So this is the direction of current flowing after 180 degree turn. Now with the help of commutator segments, what I am doing here is I am connecting this terminal here and this terminal here. So as the plus is connected to minus and the minus is connected to plus terminal before like this, the current is going to reverse. So generally if you see here, I am just changing the armature terminals with the help of commutator segments, because the commutator segments are revolving along with the armature. So when every time when they are perpendicular, the plane of rotating of this coil is perpendicular to the magnetic flux lines, the commutator segments keep on switching. So the switchover takes place whenever the coil is perpendicular to the magnetic flux lines and the brushes remain stationary. So here actually what is happening is, already know by reversing the current it is minus plus, and again by switching over the armature terminals, by switching these commutator segments, again you are having this as plus and this as minus. So again the same current polarity you can getting by switching over these commutator segments. So again you are having the positive DC output. So this is all about the working principle of your DC generator. I hope you understood well. Please subscribe to the channel. Thank you.